Okay, so now we're going to do a discussion on chapter 9.3, which is on separable equations. And the separable equation is basically a differential equation that looks like this. It's dy over dx equals a function of x times a function of y. So it's important to note that this function of x is only in x, whereas this function of y is only in y. Only in x times only in y. Alright, so now once we have this sorted out, what you want to do next is you want to separate. So to separate this this differential equation, we'll cross multiply and cross divide basically. So right here, this dy tells us that we want our y's to be on the left, and we're going to basically multiply dx to that side so that our x's are on the right. And essentially what it looks like is this once you've separated. So it'll be f of x dx, and then if you cross divide that g of y, you get 1 over g of y times dy. And now what this should kind of remind you of is integrals. We're just kind of missing the integral symbol. And we can actually do this. We can integrate both sides of the equation. So now we have integral of 1 over g of y dy and the integral of f of x dx. Then we can antiderive, but of course depends on the problem. Now we'll see an example of that. Okay, so here in our first example, this is an initial value problem. And we're going to take a look at y prime equals xy quantity squared. It doesn't look separable right now, but if you distribute the square into each of these, now we have a function of x multiplied by a function of y. We can separate. Also, notice y prime is just the prime notation of dy dx. dy dx, by the way, is called Leibniz notation, if you remember from class. So I'm going to multiply so that all the x's are on one side, and then cross divide this so that all of our y's are on the other side. Now we're going to antiderive, so we're going to integrate. Okay. Now to integrate this in particular, on the right side, it's pretty simple to do. You just use power rule, and you get plus c. On the left, it's similar. Notice that, let me write it off to the side here. The integral of 1 over y squared dy is the same as the integral of y to the negative 2 dy. And I'm going to write it like this, of course, to use power rule. So we're going to add 1 to the power, so we get negative 1 as a new power, divide by the new power. So really we're left with, well, I guess negative 1 over y on the left. Okay, now you're probably expecting me to write plus c here also. If I were to do that, so let me just show you real quick what happens. So if I were to write plus c, these are not technically the same c's. So to emphasize on that, I can call this one c1 and this one c2. But if I subtract c1 to this side, c2 minus c1 is just another constant, just call it c. So long story short, all we're really doing is just not writing c on this side, only writing c on one side, and we're able to do that because even if we wrote c on each of them, subtracting it just gives us a new constant. So constant minus a constant is a constant. And this is something to keep in mind. Any operations involving constants will just produce a new constant itself. And we'll see this a lot in this section anyways. Well, we'll see it I'm only going to do a few examples, but we'll definitely see it. And we haven't even solved for c yet, have we? In fact, we haven't even solved for y. So, the tricky thing is we can actually use this initial condition at any level. So if I wanted to right now, I can plug in x equals 0, and this will tell me that y is going to be equal to 1. This basically says that when x is 0, y is 1. Y of 0 equals 1 means that. So if you wanted to do that right here, we can say since y of 0 is equal to 1, this will imply that negative 1 over, well, y will be 1 when x is 0, is equal to 1/3 is 0 cubed plus c. Basically, c would be negative 1. So that our equation becomes negative 1 over y equals 1/3 x to the third minus 1. Okay, I'm going to clean this up and write it over here. Okay, so it's cleaned up. Negative 1 over y equals 1/3 x to the third minus 1. Now what we want to do is solve for y completely. So we have y as a function of x. right now as is, this is implicitly solved for, but to explicitly solve for y, well, we can negate both sides and then reciprocate to get y by itself. I was going to say we could write this as one fraction, to write 1 as 1 over 1 and then multiply by 3, so it's 3 over 3. And then combine, so we'll get x to the third minus 3 all over 3. This would be equivalent. So then after you negate or reciprocate, you get something. But that's one way of doing it. I'm going to show you another way of doing that actually. So instead, let me erase this real quick. So instead, let's do this. Let's multiply both sides by -1. So that'll cancel this negative. So we get 1 over y is equal to, that'll change these signs. So we get -1/3 x cubed plus 1. So I guess we could write it like this. 1 over y is equal to 1 minus 1/3 x cubed. And then reciprocate both sides. So take them to the -1 power basically. The reciprocal of 1 over y is just y. The reciprocal of this is 1 over itself. And now to get rid of the whole fraction in a fraction situation, if you'd like, we can multiply the top and bottom by, well, whatever is going to cancel this denominator, which is just 3 itself. So on the top, we just get 3, that's fine. But on the bottom, we actually have to distribute. Distributing into this 1, we'll just make that a 3 for the first term. Distributing into the second one cancels this and just purely gives us x to the third. So in total we have y now as a function of x is equal to 3 all over 3 minus x cubed. Okay, another example here. This one looks kind of similar. I probably could have gone for something a little different, but this one's interesting because well, e is going to come out of nowhere, so we'll see that right now. First off, of course, we're going to replace y prime with dy dx, so let me just do that right away. This will allow us to start our separation process. So multiply dx to the other side, we get x squared dx. So we want to get rid of y basically, so we'll divide y. And now when we start to integrate both sides, what happens? Well, what happens is, on this side, it's just like it was before, 1/3 x cubed. We'll write plus c on this side, so we don't have to write plus c on the left. But here, the antiderivative of 1 over y is ln of y. Okay? And now, how do you get rid of ln in a... well, how do you get y by itself when you have this situation where it's ln of y? How do you undo ln? And the answer is to take both sides as powers of e. So if you do that, you take this side as a power of e and this side as a power of e. So just to rewrite it, it's e to the ln of y equals e to the 1/3 x cubed. And I was going to write plus c, but notice e to a sum of powers is just e to one of the powers times e to the other power. Okay? Now on the left, e and ln cancel and we just get absolute value of y. Okay? Here, well, e to the c, e is a constant, it's 2.71828 something. And c is a constant, so believe it or not, e to the c is just another constant. So you can relabel it as c. Sometimes people call this a reset of the constant. So you can say the constant is reset here. So I'm going to write that in front now, c e to the, and then this is 1/3 x cubed. We can make that out. Okay. And yeah, let me clean this up and write it over here. Okay, so at this point, to get y outside of the absolute values, well, just consider this. If y, absolute value of y is 2, that means y itself would have to be positive 2 or negative 2 in order for its absolute value to be 2. So similarly here, if absolute value of y is this thing, then that means y itself was plus or minus this thing. Now usually for these cases, we're just going to always take the positive one unless something specific is told to us otherwise. So specifically, let me just include an additional to this information. Y is greater than or equal to 0. Meaning that y would have to be positive. But usually we don't have to worry about this detail of plus or minus is basically what I'm saying in the context of differential equations anyways. So we'll just say y is equal to c e to the 1/3 x to the x cubed. And now we'll use our initial condition, so we'll plug in x to be 0, and let's see what happens. When x is 0, remember this is y as a function of x, right? So that means when x is 0, this is y of 0, equals c e to the 1/3 times 0 cubed. That's all 0, so that's just going to give us c. So y of 0 is c, but what's y of 0? Y of 0 is 2, so 2 is c. Plugging this back in will give us our solution. Y as a function of x is 2 e to the 1/3 x cubed. There we go. Okay, I'm going to do two more examples. The next example I'm going to do is going to remind us of what we saw in 9.1. It's going to be solving the differential equation dp dt is equal to kp given the initial condition p of 0 is p0. So this is just a model that we saw for the application on population growth. And it is actually a separable differential equation. So let's divide p to this side, so we get 1 over p dp. On this side, on the right, we're going to multiply dt. And now we can antiderive. The antiderivative of 1 over p is ln of p. Here, population is assumed to be positive or 0. You don't have negative populations, so I don't need the absolute values. And here, antiderivative of k, remember k is a constant, so you can pull it out of the integral. But moreover, the integral of k is just kt. So that, I think, is better. And then, of course, plus a constant c. Taking note of what we did in the last example, taking both sides of this equation as powers of e, and we lower the equality, gives us this. On the left, e and ln cancel, and you just get p. On the right, remember we can write this as e to the kt times e to the c, like this. And e to the c is just yet again a constant. Call it c. So let me write that in front now, c e to the kt, which is exactly what we got in the example we saw in 9.1, but the way I did it was a little harder. I didn't even tell you how I did it. I just said notice this, and I went through a few motions to come up with this conclusion. Okay, now applying our initial condition, we're going to let t equal 0. So when t is 0, remember again, this is a function of t, p is a function of t. We're going to get p of 0 is equal to c e to the k times 0. That's just 1. P of 0 is p naught, or p0. That's c. Plug that back in. Finally, it gives us our conclusion that our model, p of t, is really just the initial population size multiplied by e to the kt. We'll see more use of this in 9.4. I'm actually going to discuss it in class on Tuesday, but I'll also do a video, of course, for people that missed that day physically. But yeah, we'll see more of that then. On to the next example. Okay, so this next example is also something we saw from 9.1. I just gave you this example, and I said show that something was a solution to this, but I didn't tell you how I got it. Here, we can actually see this is indeed a separable equation. Remember, y prime we can always write as dy over dx. That's dy over dx. There we go. So now let's separate. Multiply dx to that side. We can leave the 1/2 there, I guess. That doesn't include y. But the y squared minus 1 we have to divide. So we get this. Now we can integrate this. On the right, we just go 1/2 x plus c. That's fine. On the left, it's a lot harder to do, actually. In fact, the only way I know to do this is by, well, the only obvious way I know how to do it anyways, is by partial fraction decomposition. Because the denominator actually factors as y minus 1 times y plus 1. This, of course, is a difference of squares. Okay? There is a way you can do this using trig sub. I mentioned this in class, but well, think of it for a second. You let y equal secant. Secant squared minus 1 would be tangent, and tangent squared. And then you can we can use a substitution and things kind of simplify. They simplify to the integral of cosecant, which is negative ln of cosecant plus cotangent, I believe anyways. It's a little tricky basically. But this is, I think, is more closer to the ground. So let's do this over here. Let's see if I have enough space. So I'm going to write 1 over y minus 1 times y plus 1. This is just the first case of partial fractions. So it's going to be a over y minus 1 plus b over y plus 1. Okay? And, well, we can combine this into one fraction as a times y plus 1 plus b times y minus 1. It's going to be all over the same common denominator though, so all that means is it's going to be equal to the same numerator, the original numerator 1. If we plug in y equals, I guess, negative 1, that goes to 0, so we'll get in total negative 2b is equal to 1, so that means b is negative 1/2. If we let y equal positive 1, then this will be 2a for the first term, but 1 minus 1 is 0, so the second term goes away. So that's equal to 1. So all in all, we get a is equal to positive 1/2. So yeah, so that means we can write this as 1/2 over y minus 1, and I guess negative 1/2 over y plus 1. So let's do that here. There we go. So I hope you can follow how I got this exactly. And now what? Well, now to answer to write these, it's pretty simple. Since the derivatives of the bottom are 1, you can even do a u sub. You can let y minus 1 be u separately. And here, y plus 1 be u separately. But since dy would be equal to du in those cases, there's no number you divide by. In other words, you just get 1/2 ln of y minus 1 minus 1/2 of ln of y plus 1 equals 1/2 x plus c, of course. Okay? Almost done. Almost done. They both have 1/2 in common. So this is 1/2 times ln of this minus ln of that. There is a case, there's like a particular property of logs, that if you have log of something minus log of something else, you can take log of what? Of their quotient. So log of the first one divided by the second one. Perfect. Now all we have to do is multiply by 2 to get ln by itself. I'm going to clean this up though, rewrite this above, and we'll continue. Okay, so now, like I said, we'll multiply by 2 to get rid of this 1/2. So when we multiply by 2, a few things happen. Here on the left they cancel, so we just get that ln. So ln of y minus 1 over y plus 1. On the right, we'll have to distribute, and again, a few things happen. When you distribute here, that cancels and you just get x squared. When you distribute here, you get 2c, but 2c is just a constant, so call it c. Also, I made a little mistake. There was no square, was there? That was my mistake. Okay, yeah, cool. So now, to get rid of the ln, again, take both sides as powers of e. Let me lower this equality symbol. On the left, the e and ln cancel, and you just get y minus 1 over y plus 1. And again, just to avoid all those technical details, I'll ignore the absolute value part for now. Equals, this is, again, e to the x plus c is e to the x times e to the c, and e to the c is just a constant c. So we can actually write this as what? As just c times e to the x. Perfect. Now at this point in time, we can solve for c. Yeah, I'm going to do that right now actually. So to solve for c, I'm going to have to use our initial condition, and this says x is going to be 0. So when we plug in x equals 0, into this equation, we get, well, let's see. Remember, when x is 0, y will be 2. So this is going to be 2 minus 1 over 2 plus 1 equals 2 times e to the 0, which is just, c e to the 0, my mistake, which is just c. And that's, of course, equal to 1/3. Great. So now plugging it in, we'll get y minus 1 over y plus 1 is equal to 1/3 e to the x. And I'm going to clean this up again, move it up here. Well, it's a long problem. And then we can solve for y. If you follow the previous example we did from 9.1, how we solved for c was different than how we solved for c just now. We can follow that same guidelines to solve for y completely here. Multiply y plus 1 to the other side, distribute this, and you can actually get y by itself. It's not too bad. But I want to show off something. I'm going to show you something called the Mathematicians Trick, our favorite trick. So what I'm going to do is I'm going to try to separate this so that this numerator is somehow in this denominator is somehow in the numerator. So if this was only a plus 1 here, they would cancel, and that'd be great, right? So we're going to make it a plus 1 by doing this. We're going to add 1 and subtract 1 on the top. Now the benefit of adding 1 and subtracting 1 on the top, well, let me show you what it looks like. So I'm going to separate this for a second. Okay, great. So the benefit of doing this is that we can separate the top as y plus 1, the negative 1's combined to negative 2, over y plus 1. We can separate this fraction as y plus 1 over y plus 1 minus 2 over y plus 1. Now why do we want to do that is because this is just 1. These cancel and we just get 1. So it's 1 minus 2 over y plus 1. So that's what the left-hand side is really going to come down to when we apply this trick. So let me erase this and write that up there. Okay, the next thing I'm going to do is I'm going to move this to that side by add this to this side, and subtract this to this side simultaneously. It's called a swap, basically. And we get this. Perfect. So we basically have y by itself, kind of. All we need to do now is reciprocate both sides. So far, so good. Multiply by 2. So we're going to get 2 on the top. And then subtract 1. It's looking a little sloppy, so let me rewrite it, I guess. So now if you subtract 1, you get y by itself. So let me write minus 1 and then plus negative 1. So yeah, I'm going to have to erase this and write this above. So let me do that right now. Okay, there it is, and it's so close. So all we need to do now is write this negative 1 as 1 over 1, multiply top and bottom by this denominator. So we're going to get this. Is equal to x, equal to y. Yeah. Distributing this negative gives us negative 1 plus 1/3 e to the x plus 2 over 1 minus 1/3 e to the x, which is the common denominator. And negative 1 and 2 combine to positive 1. So altogether we'll get y now as a function of x is equal to 2 minus 1, which is 1, plus 1/3 e to the x over 1 minus 1/3 e to the x. And this is the exact same thing as we got from the previous example from 9.1. Really the only difference is that there's x's instead of t's, but that was our decision. Notice the original differential equation, well, when it was y prime, didn't have the independent variable x. We just chose it to be x. If we had chosen it to be t, we would have got exactly what the previous example was from 9.1. But in any event, there that is. And that's going to end us for this section. I want to do a problem though. I want to do number 17. I was going to do it in a separate video, but you know what? I'll just do it right now. Let me erase this. Okay, so this is a problem I assigned for the homework, and it's number 17. We were going to do it in class, but we didn't have time. So I'll just, do it right now, and it'll be a part of this lecture, so I think that's a good idea. Of course, we want to separate this equation. First, we need to see if it is indeed separable. And the first thing is that there's this plus here. So it's a plus y. Of course, a is a constant, that goes without saying. X and y are the only variables, and y is in terms of x, that's what we want. And this kind of emphasizes on that because it's y of this, assuming this is an x value. That's kind of what we're doing. And there's this restriction along with this initial condition here. Okay. But again, since it's addition and not multiplication, can we really cross multiply and cross divide? Well, in order for us to do that, we'd have to treat this a plus y as one thing. So if we're going to divide it onto the side where y is, we have to divide it as one whole thing. Speaking of which, this y prime, we don't really like this y prime notation when it comes to separable equations. We prefer Leibniz notation, dy over dx. So now we can cross multiply and cross divide. So on the side that dx is going to be on, so I'm multiplying dx to this side, I want to get rid of this as well. So what I'm underlining in red is going to move on to the right side. So multiply dx to the other side, and I have to divide tangent to the other side, so that's 1 over tangent. And then of course, on the dy side of things, I need to, divide this as mentioned before. Good. Now we can antiderive. So let's do that. So we set this up. They're both different. The left side in this case is easier. It's just ln of the bottom. And again, the only reason that is because the derivative of the denominator is 1. Because if you let u equal a plus y, what's du going to be? Du is just going to be dy. So that means that this integral will just become the integral of 1 over u du, which is ln of u. So that's why we're allowed to do that in this case. Otherwise, you have to be kind of careful. But when your derivative of your denominator is a constant, or even better, 1, it's just ln of that. If it's any other constant like 2 or something, you have to divide by 2 on the outside. But regardless, you can use ln when your derivative of the denominator is a constant. We mentioned that a lot though. So I just try to clear that up all the time because it's a very common mistake as well. Okay, for the right side, something a little different. We have to use something a little different. I can write this as cotangent, and that's fine. But it's better to write this as cosine over sine. Which I think is fair because, of course, tangent is sine over cosine. Naturally, the reciprocal of tangent is the reciprocal of sine over cosine, cosine over sine. And this is just a simple trig integral. If we let u equal sine of x, you can see from what I circled here in red, this would be du. So du is going to be cosine of x dx. Perfect. So naturally, this integral will just turn into 1 over u du, and the integral of that is ln of u plus c. So on the right here, we're going to have ln of u was sine, and then we have our plus c. Remember to only write plus c on one side. We learned that already for separable equations. And good. So now let's take both sides as powers of e, and we know what happens in that case. This happens, right? E to this equals e to that, but since it's addition, you can write it as e to this times e to the c. Also, e to the c is just c, so I'll move it in front. Also, these cancel, so we just get sine. Similarly, these cancel, and we just get this. Okay. Something interesting here. The only real reason why we're given this restriction is because when x is in between 0 and pi over 2, that means x is in the first quadrant. The angle is in the first quadrant. And of course, since we're taking sine of x is being treated as an angle here, really. long story short, sine of x is always positive in the first quadrant, so we actually don't even need these absolute values. And I've spoken of this before, we're going to ditch the absolute values altogether anyways. Kind of unnecessary technicality, basically. The only thing we need to do now is actually solve for c, which I can do here, just as is, use the initial condition. So now we're going to let y equal, or not y equal, but we're going to let x equals pi over 3. Okay, now when you let x equals pi over 3, y will equal y of pi over 3, which is a. So we're going to get a plus a on the left, and c times sine of pi over 3 on the right. Now sine of pi over 3 is radical 3 over 2. So this is c times radical 3 over 2. A plus a is 2a on the left. So now multiplying both sides by the reciprocal, we get the reciprocal of radical 3 over 2, we get 2 times, well I guess 2 over radical 3 is what I should have said, but that's fine. So here they cancel out. And this is multiplication, of course, so now we get c is equal to 4 over radical 3a. Nice. Now what we need to do is plug it into our solution and then solve for, solve for y. So subtract a to the other side. So y now as a function of x is equal to 4 over radical 3a sine of x minus a, because we subtracted a to the right. And that's it. And that ends the discussion for 9.3. I'll try to create a discussion for 9.4 as well, but I'll still talk about that on Tuesday regardless. I know not many people are going to show up, but if you can show up to that. But again, I'll make a discussion piece regardless, but yeah, anyways, I'll see you all then.